Among the many hyperparameters you need to specify when implementing a neural network are the activation functions. Remember that you can choose different activation functions for each layer, but activation functions of each neuron of a given layer are identical. We are now going to see the major activation functions that are implemented. First of all, let us focus on the historical activation function, the sigmoid. Remember that in perceptron, the activation function which is used is a 0,1 activation function. One major problem of this function is that its derivative is equal to 0 almost everywhere, which makes the gradient descent impossible to implement. To apply such gradient-based procedure, we must use a function whose derivative is not always 0. The sigmoid function is a smooth relaxation of the 0,1 function. It has the same behavior in -infinity and +infinity, with horizontal asymptotes equal to 0 and 1 respectively, but has a positive derivative everywhere. Using a gradient-based method to train a network whose activation functions are sigmoid is therefore possible. The exact expression of the sigmoid is given on the bottom left corner, in which we can retrieve the expression of the asymptotes in plus and minus infinity. Sigmoid exhibit a saturation phenomenon that occurs in plus and minus infinity. Indeed, we say that the activation function saturates in an area, usually plus or minus infinity, when its gradient becomes really small in this area. In other words, it means that the updates of the gradient descent, whose values depend on the current gradient, do not vary much for points in the saturated area. From a very pragmatic point of view, the gradient descent is slow down or even stuck in these areas. As you notice, saturation is a very annoying phenomenon when training machine learning methods and deep learning methods in particular. Another phenomenon occurring in conjunction with saturation is the vanishing gradient effect. As we have seen with the backpropagation equations, the partial derivative of the loss with respect to a parameter of the network corresponds to a product involving all the derivative of the activation function from a given layer to the output. The derivative of the sigmoid activation function is strictly smaller than 1, which means that a product that involves many sigmoid derivatives is very small. Therefore, the partial derivative of the loss with respect to a network parameter in a layer far from the output layer is much smaller than that of a parameter close to the output layer. By abuse of terminology, we will say that the gradient vanishes since the components of the gradient corresponding to layers far from the output layer are smaller than that close to the output layer. Note that the vanishing gradient phenomenon occurs when the derivative is smaller than 1, so it is not directly linked to saturation. You can observe vanishing gradients even for activation functions that do not saturate. However, saturation increases the vanishing gradient phenomenon because in some areas the derivative of the activation function is close to 0, which makes the product of such derivative very small. A way to avoid falling into the saturated areas is to rescale the data and control the weights and biases in order to prevent the linear combination of the input to be too large or too small. Note that the sigmoid is not a zero-centered function. The sigmoid applied to 0 outputs 0.5. So if you have centered data, applying the sigmoid creates uncentered data, which may damage, in the end, the learning process of the algorithm. You may, instead, want to keep the output of each neuron centered in order to avoid the saturated area of the sigmoid. One last comment about the sigmoid. It uses exponentials to compute the output, which may be a bit costly to compute, in particular in comparison with a linear combination. It is not a problem for the vast majority of applications, but if you try to design a network with a limited computational budget at prediction time, you may want to think twice about using a sigmoid or an activation function that uses exponentials. The hyperbolic tangent is also an activation function which is quite popular. The shape of the hyperbolic tangent is similar to that of the sigmoid activation function, the main difference being that hyperbolic tangent ranges from -1 to 1, whereas the sigmoid ranges from 0 to 1. The hyperbolic tangent is centered, so you may not need to rescale the data after each layer in your neural network. Unfortunately, like sigmoid, hyperbolic tangent suffers from the saturation phenomenon that may occur in +infinity or -infinity. As for sigmoid, computing hyperbolic tangent is a bit costly since it involves exponentials. Finally, you may notice that hyperbolic tangent is nothing more than a rescaling of the sigmoid, and consequently, the derivative of hyperbolic tangent is 4 times the sigmoid derivative. Hence, the vanishing gradient effect may be less visible when using hyperbolic tangent than sigmoids.